I am happy today to be presenting on fine-tuning models with reinforcement learning. And I think one of the main desires here is to find ways to improve the reliability of our generative AI applications and systems. And fine-tuning is a really powerful way to do that. Now, it's not the easiest way, but it is one of the most robust and most reliable. And it's one that I think is going to be receiving more attention moving forward. So that sets us up great. And let's go ahead and dive in. So I want to start with a little bit of context. So open weight models are improving rapidly. And so much of the excitement over the last couple of years has been led by these incredible research labs releasing better and more compelling frontier models month after month. And we're seeing incredible leaps and bounds on a wide range of benchmarks. And while there's a gap between benchmarks and our real world applications, we are seeing improvements in hands-on applications as well. But there's a quieter story that's also happening that I don't think is receiving enough attention, and I think has very profound implications. We have seen open weight models also improving by absolute leaps and bounds. And when I say open weight, I mean models that have been trained and the full artifact has been released publicly onto the internet. They are free for you to download and for you to host and you to serve. And you can see on this chart that even though the proprietary models have stayed out and ahead, the open weight models are never that far behind. And they're really lagging by just months on frontier intelligence. And so when you add that up over time and you consider that compounding, this means that we have access to near frontier performance and intelligence for an absolute fraction of the cost. The other incredible benefit to this is these open weight models are accessible for us to be able to fine tune. So you can start with a really high level of performance and then apply fine tuning on top of that. And these open weight models are highly competitive. And I'll admit, they are not the top performing models today. And so this is pulled from a very recent leaderboard. And you can see that GPT-5 and Grok-4 and Gemini 2.5 still dominate the leaderboard. But I want to illustrate that GPT-OSS-120B and Qwen3-235B are now placing in the top 10. So this is an incredibly competitive space. And will we anticipate the proprietary models to continue to lead and continue to really push the frontier? We should expect these open weight models to also continue to improve. And so this puts an incredible amount of intelligence at our fingertips. And we really are approaching a point where the cost of intelligence is plummeting and is gradually approaching towards zero. And the other story here is that small models are catching up. So yes, the best performing open weight models I just showed you are 120 billion parameters and 235 billion parameters. Those are large. Those are not easy to host. But I'd like you to take a look at this chart and you will see that the gap that we used to see between these large and small models has really closed. And the improvements that we've seen on these large models over the last couple of years is really impressive. But look at what's happened since even March of this year. These tiny models, less than 4 billion parameters, used to be really hard to work with, right? They were scoring at a level of 15 on this composite intelligent index. Look at these leaps up to 40. That's really where the largest models were performing in January of this year. So that gap is narrowing. And this is a whole sequence of innovations that are continuing to drive this. We're getting better at distillation. We're getting better at quantization. And as we are continuing to advance the frontier models, we're finding better ways to then extract that and condense that into smaller and smaller form factors. And this is exciting. This is moving towards more intelligence that we can deploy on the edge, on mobile devices, on laptops. And so expect this trend to continue. Now, this does not mean that we're getting to universal high performance across our models. And your price, performance, and value may vary widely. And so this is my buyer beware slide. You can spend a lot of money for a really expensive model that doesn't work all that well for your use case. You can also find really affordable models that will work really well for your use case. And similarly with the open weight models, I'm not saying that all of them are good. Many of them are not. And so you do need to be a little cautious. But if you are willing to pay attention and track the leaderboards and take some of the most promising models and assess them on your use case, you can find high-performing models that will work very well for your problems and your context at a tiny fraction of the price. And so this is good. This is going to put more competition on the labs to be able to keep providing higher quality at lower price. And remember that benchmarks do not tell the whole story. And many of the labs are perhaps over-optimizing for the benchmarks. So make sure that you evaluate for your use case. You might actually see widely different performance across the different models due to different training recipes and different training data. So evaluation will be your friend. So let's stop and think a bit about choosing a proprietary versus going after a fine-tuned model. So I recommend you always start with proprietary models. We now have access to frontier intelligence with a simple API call. You don't need to worry about deployment. You don't need to worry about training. And what this is doing is enabling greater capabilities and intelligence for a much wider range of teams and companies. You no longer need a giant machine learning organization and all of that infrastructure that it used to take to be able to do machine learning at scale. This is bringing intelligence and making it much more accessible. But it does come with some costs. It comes with this strategic dependence, and you do at least get lower costs at scale. I'd also like to refer back to a fantastic point that Chip Wynn made in her opening keynote, that if all of the companies are depending on a small number of research labs and a small number of APIs, there's very little differentiation. That's a commoditization layer. And so, yes, you can do additional work with context engineering and RAG to better personalize those results. But if increasingly the model is the product, then choosing to take that significant of strategic dependence, choosing to accept that degree of commoditization is a really important strategic question that each organization needs to think through carefully. Now, making that decision to move over to fine tuning, it comes with a lot of benefits. It allows you to own your own model. It allows you to adjust and modify it to make sure that it works well for your use case. It comes with some ongoing training responsibilities and deployment overhead, of course, but you also get more privacy and more security if you handle it appropriately. It also allows you to get outperformance on your tasks. It's possible that you're working on something that is not that important to the big research labs. If you need better performance on a domain-specific language, if you need better performance on your particular area, going to fine-tuning can allow you to really focus and drive performance on that task that's more important to you than anyone else. It gives you much greater control over knowledge and style, and it can give you lower costs at higher scale. Again, if you're starting out, small number of API calls, stick with the big models. But as you start feeling the pain of cutting larger and larger checks out to the big model providers, then it might be time to start making the investment into open weight models and fine-tuned models that might work better for your use case. Now, let's talk about the difference between RAG and fine-tuning. RAG is a fantastic technique because it allows you to adapt very quickly. It allows you to bring in your dynamic context, your dynamic information. And it allows you to pull quick API calls, say pull in information about that particular case, that particular customer. It allows you to pull in real-time data. And so that adaptability is really great. And it comes with no upfront additional training investment. It's great for lower query volume. It's also very good for knowledge-heavy tasks. It allows you to augment the domain, the knowledge and awareness that has been trained into those model parameters. But if you find yourself continually adding similar information, similar instructions, I think this is probably an underappreciated aspect of these language model and generative AI applications and systems is in practice, I see prompts grow over time. we tend to add more instructions, more context, more details. We're not as good at going back and cleaning up and removing that information. And so the longer your prompt gets, that's more computation, that's higher cost, it's higher latency. If you move over to fine tuning, you can take that information that you want to add every single time, and through fine tuning, update those parameters and really bake that additional information more deeply into your model. And so this works much better with higher volume and when you need to reason more deeply over that information that you've pulled. So where exactly is this cost break even? It depends on a few factors. It depends on the size of the model that you need. That depends on the complexity you're working with. I know Nicole spoke at some length about choosing large versus small models. Fine-tuning works for any size and scale, but of course it's going to be faster, it's going to be cheaper, and it's going to be easier to do this on smaller models, and then it's going to be more affordable to serve. And one of the benefits of working with fine-tuning is it allows you to really find and calibrate which model is going to work best for your use case, and it's going to give you that optimal performance. One other big algorithmic innovation that's come through recently is low rank adaptation. So rather than needing to do full fine-tuning on every single parameter in your model, which measures in the billions, we can use this technique called LoRA, where we use a dimensionality reduction technique. And effectively, we add in this matrix approximation. So we freeze the vast majority of the weights in the model, and we only learn that low rank adaptation. It's a much smaller number of parameters that we can tune over, so it's more computationally efficient. And you can also efficiently host and serve multiple LoRA adapters. And so you can even reduce your costs for serving multiple models this way. But it's a really useful technique that allows you to get more performance with lower costs. And of course, it's tunable. So that inner dimension, what dimension you are shrinking down to, you can keep that higher in order to get better performance, or you can make it smaller to further compress and make it faster to train. So thinking about your data requirements, let's say you've now decided that you want to move to fine tuning. What I want to say is the volume that you need to fine tune has come down. Now, pre-training, of course, requires an enormous amount of information and data. Supervised fine-tuning at the really large scale also requires quite a bit of work. But now when you want to adapt in just your particular domain, quality is much more important than quantity. All things being equal, more quantity will help. But I've been very surprised to see how much just a few dozen to a few hundred examples can really dramatically improve performance on a domain that model is not great at working with in the beginning. The other thing is, if you can, mining for production is a much more effective manner. I've heard a few of the presenters talk about this earlier, of how do you close that flywheel? How do you close that loop? How do you learn from failure modes? Well, this is a great opportunity to extract out those cases that are not working, really specify what type of behavior you hope to see, and then send those back in for fine tuning. This only works for some cases. I know certain domains are very sensitive about training, but if you work in a domain where you can feed those samples back in, it can be a really powerful technique to allow you to solve this problem at the model level, rather than having to spend the work tweaking prompts and trying to maintain that over time. So many of the big model providers work through a few different training steps. And I'm going to move a little quickly here. I want to make sure I save us some time. But typically you need to go through pre-training, instruction fine-tuning, preference fine-tuning, and reasoning fine-tuning. And that reasoning fine-tuning is typically with reinforcement learning. And this is the technique I'm going to focus on because it is the one that has led to some of the most significant advancements. If you think back to that significant leap up we saw around last year from the proprietary model, that came from O1, that came from the shift of adding in a grader based on verifiable rewards. So supervised fine-tuning is great if you have a clean set of input-output pairs. It's a great place to start. When you shift over to reinforcement learning, you now need a grader. You now need an ability to assess every single type of output that comes from the model during training. But if you can do that grading effectively, It allows you to really extract a lot more information. You get more juice from every training sample. It comes at more computational cost, but allows you to typically build more robust models that can handle a wider range of inputs more reliably. Now, preference tuning is still incredibly important, and reinforcement learning with human feedback and direct preference optimizations are fantastic techniques to do that. Those tend to be better when you have training data that consists of multiple outputs and a preference coming from typically your users of A is better in this case, B is better in this case. When we move to reinforcement learning with verifiable rewards, this is a way for us to tell the model this was correct and this is wrong. Now, this is incredibly powerful for shaping the outputs and for ensuring that our model is actually solving the problem in the correct way and in the way we want it to be solved. It's incredibly useful for code generation. It's great for structured outputs. It's incredibly good for tool use. Qwen also mentioned that choosing which functions to call and how to use tools is a valuable use case. That sets me up very nicely. That's exactly the problem that I'm going to focus on here. And in reinforcement learning with verifiable rewards, we take our training data and we pass those into our current model. Here that's represented as the policy box. From that model policy, we generate multiple completions, also known as rollouts. We grade every single one of those. And that goes through this verifiable reward box. It returns 0 if it's a failure, or alpha, which is some reward if otherwise. Now, you probably want a scale of multiple types of rewards. You can use binary, but having intermediate rewards can really help with more stable training. I sometimes get asked if you need an upper limit, if this has to be 0 to 1. I typically use 0 to 1 because that's easy for me to reason about. But given the way the optimizer works, it really is unbounded because the rewards are relative. So if you want to use much larger numbers, that's actually fine and won't interfere with the training process. We typically use group relative policy optimization. This is a relatively new but much more efficient new algorithm for doing reinforcement learning based training compared to the prior version of proximal policy optimization, which came from more traditional reinforcement learning for optimizing sequences using a value model to help compute the advantage. With group relative policy optimization, we're able to do away with the value model, and instead we compute multiple rollouts, and then we compute the advantages relative to the other rollouts. And so typically you need a few more rollouts for this, but you're saving trainable parameters and you're saving memory, which is really important for fine-tuning these larger models. So I'll walk you through an example here, but I've taken something called the Glaive function calling v2 dataset. This is one of the best function calling datasets out there right now, and it comes along with a sequence of interactions with the user, interacting with the assistant, with ground truth examples of what function should be used, and what parameters it should be used with. So I took this data set and I implemented a grader based on reinforcement learning with verifiable rewards. And I've put together a compound grader function that operates over creating valid JSON, outputting the correct function for the current context, and additional rewards for each of the arguments, and then some additional penalties if it's missing a function call at all. It's not particularly complex, but I think what this illustrates is it gives you a lot of control to specify exactly what behavior you're looking for, and then to shape those model outputs to get exactly the reliability that you determine that you need for your use case, but you still get to benefit from the vast number of parameters and the deep ability to understand context that these language models come with. I then specify our training configuration here. I'm using the Hugging Face Transformers library. It's a great library. It's entirely open source. And my source code also includes some scripts in order to set up the environment and then train your model. Here is my reward curve. And you can see we go from a very poor performance at the very beginning to getting consistently answering the function calls, as well as getting most of the parameters correct over time. Always watch out for rapid spikes in the reward, which can indicate reward hacking. And this is the model finding a way to get a lot of reward without actually solving the solving the problem that you intend. Don't be surprised if it happens. These models are really good at getting high rewards, even if it's going around your intention. I will skip over the hyperparameters here just in the interest of time. But what I'll leave you with is always start with proprietary models and start with context engineering and RAG. It's faster, it's easier, it gets you to a product experience quickly. But really consider moving over to fine tuning as a way to improve performance on your use case, reduce cost, and give you more control. Remember, the big model providers are telling us to only trust them and rely on their models and their APIs. But when it comes time for them to design and ship their own product experiences, most of the time they're doing additional fine tuning to get better performance and better results because they know that that's an important part of their moat. And so I encourage all of you to think about what your moat is on your team and think about the data and the training process and the grader. All of this is something that can help give you better performance. And it's something that can create enduring value and create that better performance over time. A new, better model comes out, great. Now you can start with that higher foundation and still pass it through that same training regime that you've built. And one last thing, if you've enjoyed this presentation, my book, Building Applications with AI Agents, this is my first book, is now available on the O'Reilly platform, and it is also available on Amazon.